Aus- und einstecken bringt nichts. Dann mache ich es damit schlimmer.
Der ist schon wieder about. Okay. Das ist hoffnungslos. Das ist hoffnungslos. Sieht gut aus. Okay. So. Müssen wir kurz gucken, ob wir Ton haben. Sekunde.
Die Kamera.
1, 2, 3. Yes.
Die Kamera.
Kamera, ja, Kamera ist hier. So. Okay. Wunderbar. Okay. So. Welcome again. Thank you. So many slides. So. So, okay, we come to the second part of the meetup. So I hope you enjoyed the break. Yeah. How did you like the food? Really good. Yeah. Sometimes really good to have a meetup, not with pizza. Thanks, Franco, for sponsoring, not pizza. So really good. Now we come to the second part, talk by Florian about Dask DataFrames, Dask DataFrame. Dask DataFrame is fast now, and afterwards we have the lightning talks. And so we have 3 lightning talks, one by Tim, a case study of custom kernels, one by Natalia, find the best strategy to get involved in open source, and one by Lisa, legal argument mining from court decisions. A flyby. Who knows lightning talks? Oh, okay. So lightning talks is a 5-minute talk. You can talk about anything appropriate. Yeah, but it's 5 minutes. There's no Q&A. It's 5 minutes, and you have to stop 5 minutes no matter where you are in your talk. We stop it after 5 minutes. That's the thing with lightning talks, but it's a great way to start doing a talk in the community, just going, and thanks everyone who contributes a lightning talk today. So, and now we don't have community announcements, we already covered it, so now welcome back, and now welcome Florian, who will tell you a lot about Dask.
Thank you. Yeah, so I'm going to talk about Dask DataFrame specifically. This is only a subset of what Dask can actually do. I assume a certain familiarity with Dask, but if you are not familiar with it, it's a parallel or distributed version of pandas. If you maybe know Spark better than Dask, we are like Spark, but better, and Python only. And a part of this talk will be dedicated to basically solidifying this claim. So let's get started. First of all, who am I? I'm working at Coiled. Coiled is a commercial entity behind Dask. We are doing maintenance, support, and most importantly, we are offering a hosted cloud product so we can launch Dask clusters or any Python computation really in the cloud very easily. Very, very short demo will follow shortly. I've been involved with Dask, the open source project, since 2013, and ever since I've, progressed on this trajectory, started at Coiled, and I'm still involved in the project. So my job is literally to build open source software, which is great. Now, this talk will primarily have 2 sections. The first one will be about Dask DataFrame improvements, what happened about the past 13 months. So whoever tried Dask before that, I'm sorry, I feel you. It's better now, I promise. If you are not familiar with Dask, just believe me that it's incredible what we did. The second part will be about, now that it's fast, we are actually looking and comparing us against different technologies. And spoiler alert, we are not better than everybody else. And lastly, very, very mild outlook into the future. So Dask DataFrame 2.0, it's different than before. What did we do? And first, let's do a very brief demo to show you how bad it was in the past. I'm running a query that's a TPCH query. That's the benchmark suite I'll be talking about later. For those not familiar, I'm basically reading a couple of data sets, applying a couple of filters, performing merges, joins on that tables, and doing some analytic stuff. So pretty standard thing, really. what I'm executing this in the cloud, and this is where basically my company comes in. So Coiled Clusters, that is launching a Coiled cluster, a Dask cluster in the cloud on AWS in this case. This is currently scanning my notebook for what I'm having installed, and is replicating this in the cloud such that I don't have to fuss about Docker images or anything like this. This takes about a minute now, and then we can actually have a look at the Dask dashboard, and I will just show you how I execute this query on Dask. And this is now the legacy version of Dask, so this will be a little bit painful. Frankly, we will not even see this finish because this will probably run until almost the very end of this talk, so we will switch over to the newer version in a second. But still, I want you to appreciate the slowness just for a second. And all the red and yellow stuff. So for those who are familiar with Dask, you will maybe have PTSD. I'm sorry about this, but this is for the greater good. This boot up time is actually a little bit slower than I wanted it to be. So I will just jump over to the newer version, make sure that this works. Of course not. So I will restart this very briefly. And we'll head over to the other one. So this is now up. Familiar Dask users know this dashboard. You will see a lot of colors now. I'm executing this query. This runs in the states where our data is living. So this will take a second to actually kick off. All right. That's the trouble with live coding, isn't it? Well, I'll continue in the interest of time. I don't know what went wrong. But what you should have seen is on the old stuff, a lot of red, a lot of yellow, workers running out of memory. Eventually, it should have completed this exact query. On the old one, should have run about 950 seconds. On the new one, 50. That's an improvement of about 19 times faster now without any modification of the code. This is just a newer version. Same hardware, same everything else. Now, what did we do? There are a couple of things really. One is actually that we are using PyArrow strings, for instance. Most of the data have string data types. This is extremely inefficient. It requires a lot of memory, especially in a distributed context. This is very, very bad. So they are much, much more performant, require much less memory. And this is something that Dask is now doing by default, actually. If you're using something like pandas, you are still not benefiting from this by default. This will be something that I believe will come with pandas 3, just like other benefits we are using, like copy on write. I can talk about all of this. But suffice to say, these kind of PyArrow strings, and this is just a toggle, so you can also opt out if you have issues. But this is gaining us, like in this example, it almost halves our memory, and in a distributed context, this speeds everything up as well. What's also interesting is we developed a new shuffle algorithm. A shuffle is actually something that's in a distributed context, so I'm not talking about shuffling cards, randomizing stuff, but quite the opposite. Frankly, I don't know why it is called a shuffle, but this is the kind of process of ordering data in a remote context, like sorting keys into partitions, and this is the very fundamental operation. We need to join tables or to sort tables and all of that. And I won't go into details here. This is some algorithmic foo here, but this is a very complex operation. In fact, if you do it in a, say, even in a smart way, you end up with many, many intermediate tasks, very many connections between your tasks. This is actually quadratic runtime, which is very, very bad. What we did is we encapsulated a lot of this stuff into lower levels of our abstraction, and we call this P2P shuffling. So basically, our leader in our system is getting out of the way, and all of our workers, so Dask has many, many different workers, they can do this shuffle operation autonomously. And this saves us an incredible amount of time. Also, many integrations, like the previous version was just awful. This is now shuffling in constant memory. So if you ever encountered out-of-memory situations with Dask, this is very likely gone with PyArrow strings and this P2P shuffling method. At least I haven't seen many or any complaints about memory usage since. But the most exciting thing now, and this has been missing from Dask for years now, is that we now have an optimizer. So we don't execute what you type literally, but we take the meaning of what you typed, and then we translate it to something that is actually sane. So we make it easier for you to run efficient code, and I will present this in two, say, simple examples, and then we'll go into more sophisticated ones. And the two most prominent things are called column projection and predicate pushdown, which means select a couple of columns or provide a couple of filters, like column A larger than 1. How this looks like in Dask, we typically now define a computation as an expression graph. So the code on the right-hand side, where you can see, okay, I'm reading two data sets, orders and customers. I'm merging them on a specific key. Maybe then I will filter on a specific date. And finally, group by and calculate a sum. I think this is a very straightforward example, very simple. Most real-world examples are more complex, but this creates an expression graph like this. This is what you typed. Now the optimizer goes over this and rearranges stuff in a way that actually makes sense from an execution point of view. Like, we don't have to load all the data. We just have to load the kind of columns that you requested for your query. And the filter, we don't have to join all of those tables, but we can push that filter further down the execution stack. This is also what every database really is doing. Like, if you are typing a SQL statement, this is what every database, at least every database I know of, is doing as the very, very first step. It rearranges whatever you are typing to push filters down, to push projections down, such that you have to move much less data. And this is, I think, an intuitive example of what this optimizer can do. It can rearrange things. It can also insert new expressions, and so on and so forth. And I will show examples about this in a second. Another thing, and this is not necessarily about rearranging expressions, but this is something new. If you've ever worked with parallel computing on small, medium, or large data, you very likely encountered a partitioning problem. The partitions might be too small, they might be too big. And after what I just told you, after pushing filters down and columns down, even your knowledge about how big your files are, that's gone now, because what you're actually loading might be smaller. So by our optimization of pushing filters down and column protections down, we might actually mess up your partitioning. You might have constructed a beautiful data set, but then we optimize things and your partitions are tiny again. And this is exactly the knowledge we can put in now here. Most data set ETL workloads are actually running on Parquet data sets, where we have knowledge about the sizes, knowledge about the columns, and much more. So depending on what kind of computation you are running, we actually know how big your partitions should be, and we can repartition it automatically. So a lot of, say, we actually have to overhaul our getting started or best practices guide, because most of it doesn't apply any longer, because we're doing it for you now. That's the entire intention of this optimizer. Encode best practices such that you don't have to. Make it easier to work with Dask. Another one, and this is actually much less trivial, but consider a more complex query. Like, I'm reading now 3 data sets. They're called light item, part, sub. This is part of the TPCH data set. Don't worry about that. But we are joining all of them. And as you notice, they are joined on the same partition key. So that looks like something that we should be able to leverage. And by default, this is not leveraged at all. Like, the trivial computation graph looks like this. We take 2 tables, smash them together. Then we take the result, take the 3rd table, smash them together. And that's actually 4 shuffles. So every arrow basically represents a very expensive version of the shuffle, where we have to take all the data, redistribute it on all the nodes. So this is every time a step where I have to hold the entire data into memory. Some engines claim they can do this with, not having all the data in memory. I don't think that's very difficult, especially in a distributed way. So either way, reducing shuffles is something we are striving for. And this is one of the examples where we actually take your expression graph and modify it in a actually non-trivial way, because we are inserting one of those expensive operations explicitly, such that both the left output and the right output have the same alignment. They are sorted by the same key. And in the end, the smashing together is actually trivial. So we have to move your entire data set, which can be terabytes of data or just a couple of megabytes, depending on what you're doing, but we have to do it less. And this altogether makes us much faster. This is the example of query 3 I wanted to show you, where the initial runtime was 950 seconds. So the legacy version was about, say, the beginning of 2023. I think the shuffle operation, so this is not a timeline representation, unfortunately. We released this in February 2023. And ever since, we rolled out many more changes. So there are many changes that are not shown here. But overall, these are the big steps we did. And now you get all of this for free. This optimizer is now on by default for all DataFrame computations. There are a couple of kinks there still. You can opt out of it, but frankly, we are fixing everything as fast as we can. And every user I know of has a better experience with this. So this is what we did. If you knew Dask 2 years ago and dropped it again because it wasn't fast enough or just ran out of memory, please give it another shot. Once we did all of that, we wondered, how good or bad are we actually? There are a couple of very big new players like DuckDB and Polars, and there's Spark, which is known to be excellent at large-scale data processing. Well, yeah. What's there to say? I don't like Spark, just a disclaimer, also because it's not Python, but I try to not be biased too much by this. Everything else runs in Python or Rust, so that's great. So let's have a look at this. First of all, TPCH, I mentioned this before. This is boring methodology. This is not actual TPCH, so we cannot publish this officially. It's stored in Parquet, etc. We're talking about different scales. This is something I would like you to understand. The scale means this is the biggest table we are using. Like if I'm running a 10 terabyte scale benchmark, this means that the largest table involved, and I'm going to join much more on it, that's 10 terabytes or 100 gigabyte. And we are running this on EC2. We are running this on Coiled, what I've shown you before. Coiled can run all of those engines, DuckDB, Polars, even Spark. Yes, we built a Spark integration. It was not a pleasant experience, but well, let's continue. Yeah, DuckDB and Polars, they cannot do distributed computing, so they ran on a single, very beefy, very large virtual machine. This is also a limitation of them, of course. Anyhow, this is a little bit messy, I apologize, but what I want you to take away from this chart, this is actually running on a 100 gigabyte data set on a relatively large machine with 64 CPUs and a quarter of a terabyte of memory. This is all over the place, really. You can pick out that something like DuckDB is actually pretty fast, but if you look at individual queries, sometimes Dask is faster, sometimes DuckDB is faster, sometimes Polars is faster. But Polars is struggling really hard. There are a couple of queries where Polars just didn't finish. It just ran and ran and ran and ran. We actually noticed that whenever Polars hits many joins in sequence, it never finishes. It didn't fail. It just computed, it swapped to disk, CPU ran hot. This is also why we haven't looked at Polars. But for this data size, I think it's important to note, there is no winner. And we will talk about comparisons to DuckDB and Spark in a little bit more detail, but every engine has its benefits. So we are not faster than everybody else. I'm sorry about this, but we are better than Spark. So let's look at a couple of details. DuckDB is, I think, a hot favorite for many people. DuckDB is lightning fast. And what I'm not talking about right now, we also did tests on a local MacBook, for instance, on this very MacBook, actually. DuckDB is lightning fast, I promise you. I'm not showing you the data, but if you are, say, working on relatively small data on a relatively large size, DuckDB and also Polars is incredibly fast. But I'm looking at larger scales now. So keep in mind, DuckDB has to run on a single virtual machine, so there are physical limitations. We didn't buy a 10 terabyte host for this benchmark. I'm sorry, we could have, but we didn't. And what we saw is actually that it's still a mixed bag. DuckDB is known to be lightning fast, and it is for local machines, but once we move to actually large data processing tasks, it's a mixed bag. So sometimes Dask is 3 times faster than DuckDB, and sometimes DuckDB is just, well, 50%, 100% faster than Dask, but there's no clear winner. The TPCH benchmark, there are 22 queries. They range from very different workloads, from just reading I/O to very complex analytics. So it actually depends. What are you doing? What's your purpose? What's your data? DuckDB is not strictly faster than Dask. It all depends. And this story actually continues to much larger scale. Like if we scale up to 10 terabytes, and I just assume few people are actually running on the scale, but DuckDB fails because it has these physical host limitations, even when spilling to disk. So DuckDB fails in many cases, so we don't have any comparisons. And just like in the case before, Dask is sometimes faster, DuckDB is sometimes faster. It depends on what you're doing. But what we can see, Dask just failed in one of those queries. And this is a trend we can see actually continue over the next couple of plots I show you. Dask just finishes. Dask pulls through where other engines fail. And we'll now look at Spark, my favorite. And Spark is, most of the cases, actually pretty slow. And this was surprising to us, because Dask or Spark was known to be the fast engine for data processing, large-scale data processing, and it isn't really. At least this is not what we experienced. This is running on our own deployment. We are publishing the configuration. Actually, all of this data will be published today or tomorrow, if nothing goes wrong. This is running on Coiled. We also tried it on Databricks, for instance. The numbers changed a little bit, but not by a lot. And if we move to larger data, we also have to move to a larger cluster. So, on 10 terabyte, this is a very different story. Spark just couldn't compete anymore. We actually had to increase. We ran similar tests on much larger hardware again, where Spark could finish the stuff, but it wasn't actually faster. It was still slower. We saw that it is around about 20% slower. Again, it depends on what kind of use case you're looking for. As you can see, there are also a couple of queries where Spark outcompetes us. Again, it depends on what you're doing. It depends on your data. But in general, Dask is actually much more robust. And that's it, basically. There are a couple of, say, decision factors you have to weigh when you decide what kind of technology you are using. Like DuckDB is lightning fast on actually a wide range of scales. Even on 10 terabyte, it was pretty fast, but it was not very robust. Polars disappointed us to a certain extent because it failed as soon as it hit, say, memory limitations. And Spark, I don't have time to talk to you about my experience when running this. This was awful. It failed. The configuration was difficult. But yeah, Dask is pretty consistent. It runs. Sometimes it's slower, but it is actually very competitive. We support most of the things people care about, and we have sensible defaults, which is not the case for everyone here. Now, is this the end of the story? Actually, it isn't. We just finished this up, so this optimizer is actually pretty fresh. We implemented the most sensible things that came to mind. But when profiling the workloads, especially those where we were slower than, say, Spark, we noticed that there's still significant overhead we are suffering. We profiled this, and for some of the queries, half of the time was spent just submitting our query because of, let's call it a bug in our library. And another one is the shuffle I've been talking about a couple of times. We have a prototype, and this is the bottom right corner, so blue is good, where we see a consistent improvement of about 30%. So we're just getting started. This is only the start of all of this. There are much more advanced query optimizations we can think of. And who knows how fast we will be in a year. I don't have a final slide. This is my final slide. So thank you very much.
Yeah, thanks a lot, Florian, for the talk. So I actually have a question.
Yes, please.
Can you give us some insight? Which type of queries run faster with PySpark or Dask? So what's the difference? So there seems to be some difference.
Yeah, I don't know them by heart, obviously, 22 queries. I can cite a couple of examples, like query 6 is one I put a lot of emphasis on because I rewrote our Parquet interface. So this was my optimization candidate because query 6 is actually reading a lot of Parquet data and is applying very simple transformations on it. Like if you do these kind of things, read a lot of data and maybe calculate a sum over a column, query 6 is the way to go. 18, for instance, is actually maybe the most difficult one. Is also where we actually, every single engine failed on a 10 terabyte case. It's a super sophisticated join of, I don't know, 4 or 5 tables. So this is also where join ordering comes into play, which is, well, still ongoing research subject. So it really depends. I would have to look into this. If you have specific questions, we can look into a couple of queries and I can tell you what the problem is. We looked at every single one of them at one point in time, but it's a little bit too much for me to remember.
Thanks for the talk. One question is, I know it's an unfair comparison because with Snowflake you can't really control the warehouses, but the obvious question is, have you also evaluated performance with Snowflake, and if so, do you have a rough feeling how it would perform for similar warehouse sizes?
I don't. We didn't compare it against Snowflake. I think the comparison is not very fair, as you say. Snowflake is actually a fully fledged data warehouse management layer. I honestly don't know.
Here's no
Hi. If I understood correctly, you're using PySpark, right?
Yes.
Do you think there is a difference if you use what is it, Java Spark thingy?
Yes and no. So what we've been using is the PySpark interface, but we've been using the SQL interface. So the SQL stuff is just basically shipped to whatever control plane Spark is launching. It's, I think, called a driver, and that is evaluating the SQL statement. So in the end, it is using Scala. We are just using the Python interface to submit that stuff. I would assume that if you write, say, optimized Scala code without using the SQL interface, I'm very sure you can beat this performance. I also know that Spark has about 200 configuration knobs. You can make it faster, I promise you. That's beyond me. And we even talked to some experts. We talked to, for instance, a startup that's specialized in optimizing Spark. They couldn't help us either. So optimizing Spark is definitely possible, but this is a challenge.
So Dask has been around for many years now. Why did you start developing this optimizer features so late? I assume many people have already settled with Spark or even started using Polars and DuckDB. And I assume there could be many more users for Dask if you started developing these features earlier.
Yes, absolutely. I think the question to this is not very trivial. So Coiled, for instance, as a commercial entity who's by now funding feature development, hasn't been around for that long. So it's been an open source project that was fueled by volunteers. So it's very difficult to get these kind of projects on the ground and executed. That's one part. Another one is a couple of years ago, so long before that, I think around, say, 2020, 2021, we had severe stability issues and we had to rewrite a lot of our core code. So this was clearly more important, like a deadlocking cluster. No matter how fast your code is, if it just stops working, this is an unpleasant experience at best. So we had different priorities. We had not a lot of funding back then. And once it became stable, so it's now rock solid, we had time to look at this. And the development has been actually going on for probably 3 years now. So these were very challenging projects.
Thanks for the great contribution. My question is about the optimizer.
Yes?
How did you decide about the optimizer, especially in the partitioning optimization part? Have you tried different optimizer and decide for the best one? And how did you actually come up with the optimizer?
Yeah, so how did we come up with it? I think so. When we started, we actually evaluated an open source framework for expression matching and rewriting, because that felt like it was a good thing. I forgot about, I think it's called MatchPy. We then found that this is much more complex, and we decided to, or we designed our own optimizer. So the way it functions, the way it works, the way it iterates over the graph is custom. The partitioning itself is actually relatively straightforward, at least for the case of, say, Parquet data sets, because Parquet exposes metadata information that tells us how big the files are, how big the individual columns are even. So if we perform a pushdown or something like this, we can pretty accurately estimate how big the partitions are going to be and can inject a repartition layer.
Hey, thank you for a great talk. My question would be, first of all, I really love Polars, and it's like pity to see that it loses in most cases. Yeah, and my question would be, did you use lazy evaluation for Polars or not?
We actually were in contact with the author of Polars to optimize a couple of those. I think we settled on this streaming API. I'm not a Polars expert, but this is what he recommended to us. And yeah, we basically asked him for advice. We implemented that kind of advice. And again, I want to repeat, Polars performed excellently on, say, relatively small scale. So as long as it fits in memory or is maybe slightly over your memory, it's extremely fast. And if this is your kind of data and you don't intend to scale out, go for Polars.
Well, that's exactly the problem. In most cases, when you go beyond the memory, you have to optimize the types. For example, many times I see in data sets, in Parquet files, you save values like 0101 in U64, and that makes no sense. And if you had, like, while loading from Parquet, you had this operation of optimizing the type, maybe Polars could have won. What do you think?
Well, that might be true for every engine. Like, this data type optimization is not implemented in Dask. To implement something like this is actually pretty tricky.
Why is it?
Well, you don't know your exact cardinality of your data. Sometimes you do. In some cases, you can implement a specialized version of this, but not generically. But this may be one of the optimizations we might be looking into in the future. But typecasting is always a bit of a difficult topic. We can talk about this later in more detail.
I think roughly you spend your time on three things, right? It's compute and reading Parquet files and network. Do you know basically what's going on? Like, where are the bottlenecks, and what do you spend your time on?
So the short answer is yes, we do. We know pretty exactly where we are spending our time. And if I had more time, I would now give you an excellent demo of our platform product Coiled, where we see all of this data. But we are using, for instance, PySpy for profiling. We're using, the platform Coiled is using Prometheus in the backend to collect CPU and memory metrics. And Dask itself is also very, very, very rich in terms of telemetry. So it exposes many internals. So we have a very good insight. Right now, the bottleneck is shuffling again. So about half of the time on this entire benchmark suite is spent on shuffling. This also means network? Or? Yes, network. Not just network, but also network. Shuffling is complex.
So you got one slide where you compare all the different technologies, and you put down a thinking face emoji for SQL support for Dask. Can you tell us more what that means?
Yeah, the SQL interface, so there's a project called Dask SQL. Dask SQL has been around for ages. First, it was a voluntary project. A couple of years ago, it was actually picked up by NVIDIA, so they are maintaining this right now. I think the question phase is there because we are pretty biased. We don't believe in SQL. Sorry. So the support is there. It works. They are still migrating to this new optimizer. They're currently using Data Fusion. It works. I haven't had any experience with it. I wouldn't necessarily recommend it unless you actually have to do SQL. I think using the DataFrame API is more expressive, more easy to test, more easy to put, use machine learning libraries or something like this with it. So it's there, but I recommend something else. That's it.
Yeah, I have a question about.
I think we have time for like 2 more questions, and there's one also from the audience here.
Yeah. First of all, thank you for your presentation. I've got a question as I'm a data science beginner. In my university, we talked about pandas a lot, and actually pandas was crashing some other time on my end. Maybe it's a skill issue on my end as well. But would you recommend learning Dask instead, or would it be the wrong use case for?
No. If you're getting started, don't start with Dask. Start with pandas. And then once you start hating it, look at Polars, look at DuckDB, and if you actually have the need to scale out, either because you are CPU bound or memory bound, look into Dask. We are thinking about a version of pandas where we actually use that kind of optimizer for pandas workloads. That's not out yet. But just for the optimizer, I would not recommend using Dask because Dask comes with many complexities pandas does not come with.
So you would recommend generally for everybody to learn Dask who starts data science?
I personally, but I've been involved with Dask for 6 or 7 years now. Learn pandas. It's widespread. Every library integrates with it. It has some quirks, but everybody knows it. Every library works with it.
Okay.
And you can transition to Dask if you need it.
Thank you.
Yeah, there's one question from the remote audience. What's your opinion about Daft? Seems to be another contender written in Rust and partially based on the Polars code base.
Honestly, I don't know. I've heard about the project. I've never used it before. It's one of those many things that just pop up. Maybe it will be a serious contender on this table. Maybe it won't be. I don't know. Sorry.
All right, I see there's more questions, but we're already running quite over time. So I think we have a networking break afterwards. So Florian will not run away. He will stay, I guess.
Yes.
Yes, so please ask him questions in the break. But a big applause, please. Great talks, many questions. Next is Tim with his lightning talks. We start now with lightning talks. Okay,
we've a painful thing, so it didn't finish.
Yes, didn't. Right.
Anyhow, lightning talks.
So
who's first?
Talk. Well, Tim, that's a PDF. Yeah.
So view. How do I make this?
Yeah. Yeah. So, lightning talks. So lightning rules, 5 minutes. Everything that's appropriate. I think engineering custom kernels sounds like an appropriate topic to me. So let's just get the timer started. Oh, you need a microphone. Just take this one. Yeah. Good point. Yeah, you can just like clip it on. Yeah. And oh yes. Here. Thank you. Okay. Okay. On again. All right. Now let's start the timer.
Okay. I want to give a very short introduction of how you can use some knowledge you have about a data set to engineer custom kernel functions which might increase the performance of support vector machines. First, what does a support vector machine do? Given a data set with 2 classes, it finds the hyperplane that separates those 2 classes. Finding that hyperplane can be reduced down to an optimization problem, which then only depends on the inner products of your feature vectors, which is nice because you can use that to fit nonlinear data by replacing that inner product with a kernel function. So this is the topic of today's talk. Here's an example. It's the radial basis function, which is just the exponential of the Euclidean distance. And the topic that I came about quite often, even though my career is quite short as of yet, is that in a classifier, what's important is not necessarily the magnitude of your feature vectors, but more so the direction. So this is a synthetic data set I created for this purpose. And which class a vector belongs to or a point belongs to is only dependent on the angle towards the x-axis. Now you can fit a radial basis function, which kind of works, but you can already see that especially if we had a smaller data set, it might not generalize well. So our first step is using the cosine similarity, which is just uses the angle between two vectors. So instead of using our normal inner product, we now use the angle, which is the normalized inner product. So you can imagine that like projecting every feature vector onto a unit sphere, then using your linear kernel, so just fitting a plane, and then projecting it back, which produces those cone-shaped decision boundaries. Now this is already the right direction, but it doesn't work yet with the complexity of the data set. So we can now start with the engineering and take it one step further. And what we do is we use the same idea, but we replace in the radial basis function the Euclidean distance with the distance those two vectors would have if they would be normalized. And then we use the same thing. So we project it on the unit sphere, fit then what would be a normal RBF kernel, and project it back. And this way we get a decision boundary that actually works. Now we can do one final step further. If we now have a data set with the same angular dependency, but the decision boundary doesn't start at the origin. And then what I came up with is the generalized cone kernel, which is just a combination of the normal radial basis function, which is this part, and the radial basis function with the normalized distance, weighted by a parameter alpha. And alpha is chosen such that for small vectors, it favors the radial basis function, and for large ones, it favors the normalized radial basis function. So you can fit quite complex decision boundaries around the origin, and then for large magnitudes, you get a decision boundary that takes the angle into account. Thank you.
Oh, thank you very much. So, next is Natalia, how to get started in open source. Yes, microphone. Here's your microphone. Just a little tip, so best stay here, because otherwise if you move to the slides, people will just see a shadow on the video. Yeah. So, let me take the timer. Yeah, just clip it somewhere. Yeah, that's just fine.
Oops. No.
Yes. Have you?
Yeah.
Yes. It's just like you can just. Okay. So, here you go. And there's another neat trick. Look to the camera. Just look to the camera and do this until it shows a green light. Then it will follow you as well. Just like with an L.
And
The green light. Yeah. Yes, you're all set. All right. Yeah. You know, you don't have to keep it up. It's all right. It's just like hello. Yeah. We have this fancy AI camera. So, and it follows. It follows. Yeah. So yeah. Please give a warm welcome to Natalia.
Yeah. Hello, everyone. My name is Natalia, and I'm software developer with non-focus. For the past year and a half, I have been working on Python library pandas, and I am a member of pandas dev and pandas triage teams. Today, I want to share my experience how to get involved in open source. But before we begin, please raise your hand if you have ever contributed to open source project. Oh,
nice.
Yeah, nice.
Thank you.
I hope after my talk we will have a few more contributors who join us. So why open source? Very often I see developers ask, what can I get from contributing to open source, and is it worth it? For me personally, it was totally worth it. I wanted to contribute to open source to grow as a developer, but it turns out I gained much more than just developing my programming skills. Overall involvement in open source projects offers a range of benefits, such as skill development, cutting-edge access to cutting-edge technologies, portfolio enhancement, recognition and reputation, personal growth, networking, and contribution to a community and social good. Sometimes people find it difficult to start contributing to open source projects. If you're looking for open source project on GitHub that need help, it can be really overwhelming. So here are some tips on how to overcome this. You can participate in sprints. Development sprints are 1 or a few days of intensive learning and development on open source projects, usually taking place at conferences. Project maintainers will help you to set up an environment, choose an issue, and submit a pull request. Take a look at the tools you use and ask yourself what issues each one might have. Maybe you will see a way to improve them, or you could try documentation where things are unclear. Don't forget that there are valuable ways to contribute to open source beyond code. If there are open source projects you know and use, help out for others by answering questions on the mailing lists, Slack channels, Discord, and other platforms. And be involved in communities such as PyLadies, fit someone who wants to get into open source without coding as well. So how to pick out a project to start with? First, check out projects you're familiar with. Read discussions in issues and pull requests to get to know the particular style of communication and if it suits you. If you're looking for open source project on GitHub, here's a repo you can use. It's a repo with plenty of issues that a beginner could fix. Search for issues labeled help wanted and good first issue to find a suitable task. And for whatever project you want to contribute, don't forget to check if your project have a contributor guide. So when you found a project you want to contribute to, my advice starts simple. For example, fix typo. In the beginning, you might need some time to get used to the process of using Git and GitHub. So, here are some options what you can do for your project. For example, report or fix a bug, review pull requests, contribute examples to the project documentation, or propose and implement a new feature. Oh, last slide. So, when you start contributing to open source, keep going. You will certainly find a reward for doing this. And here's a short story on how different rewards can be. Then I started contributing to pandas. My task involved working on code style issues. It often meant changing only a few lines of code. But in every merged pull request of mine, one of pandas core developer left a gift with cat. Yeah. So
sorry, it's the lightning car. Sorry, but thanks so much for sharing,
thank you
and please
for
contribute
your time,
more.
and thank you, Alexander and Uwe, for organizing such a great event.
Thank you very much. Okay, next is Lisa talking about legal argument mining. Oh.
Cool.
So.
Yeah, okay.
Yeah, please give a warm welcome to Lisa.
I also need to raise my hand. Huh? I also need to raise my hand.
Yes, please.
Yeah.
Like L, does it follow you? You move a bit, then I'll reset the timer. That doesn't count. Yes, it's following you.
Yeah,
AI is following you.
Okay,
Yes.
that's
very
great.
good.
Follows
Okay.
me everywhere I go. Okay, cool. Yeah, hi guys. My name is Lisa Shalaguin or Shalagina, depending on where in the world you're from. For those who don't know me, I'm many things, but what is important for this talk is that I have a PhD in computer science from University College London in AI, and to be more precise, in intelligent systems, and a niche field called computational argumentation. However, I also hold a degree in common law from the London School of Economics, and that's why I'm interested, surprise, surprise, in legal tech. I did work on a few projects in RegTech and in legal tech in the past, and this talk is based on an article that I wrote for a German law journal called Rethinking Law. However, it's behind a paywall, and I don't want to mess with Germans in the UK. I put all my articles, papers that are behind a paywall, like on Spring, I put them out on my website, but with Germans, I'm a bit, especially lawyers, right? I don't want to mess. So that's why, I'm going to give you a little insight on what I wrote about. And however, the purpose is to draw attention to the legal tech domain, because maybe some of you have never heard of it, and maybe you want to contribute to open source projects in that domain. This is just some brazen self-promotion. So you can look me up on Google Scholar if you're interested in what I did during my PhD. And this is how the article was called. So legal argument mining from court decisions, a flyby. If you want to purchase it, then you can. Or you can send me an email and I'll send you a vertrauliche link.
For review.
Just for review purposes, exactly. Okay, so for those who are not familiar, argumentation mining has been defined as the general task of analyzing discourse on the pragmatic level and applying a certain argumentation theory to model and automatically analyze the data at hand. So I don't want to dive into argumentation theory. You can ask about that later. I want to focus more on the NLP side of things. So the three stages that are crucial in argument mining are, of course, corpus annotation. We need corpora, right, for training data as well as for benchmarking. Argument extraction, of course, the ones who label the corpora, well, they need to extract arguments either way, either manually or automatically. But then those who want to develop models who do that, obviously they need to be able to extract arguments and then also label the relations between those arguments. So if you think about a court decision, right, where two parties are arguing, right, you want to find like the relation between, the arguments of party A and how they are related to the arguments of party B, whether they counter each other, whether one may be stronger than the other, etc. So the current state of the art, surprise, surprise, we're also using LLMs now. Mainly BERT. I haven't seen that much ChatGPT yet. Also maybe because it's quite niche and there's not much, open source, just research on that. A lot of stuff is proprietary. So maybe, somewhere in like legal firms they use it, but nothing really I could find yet when you just go on Google Scholar and check the latest research. However, what is more important, this is what I want mainly to draw my attention to, is, as you know, garbage in, garbage out, right? No matter how sophisticated our models are, if we don't have proper corpora for all this and properly annotated corpora, then it doesn't matter how sophisticated our models are. And the problem is, because it's an interdisciplinary field, right? We have lawyers who don't know anything about AI and how it works, and then you have people who work in AI, but they don't know how legal reasoning works, right? And so what is happening currently is that there's a major discrepancy between the way that people annotate the corpora and then the way that actually lawyers want to use that corpora. So recent research claims that there exists, as I said, major discrepancy. In my opinion, it's correct. Between NLP and legal practitioners. So what we need to work on is obviously we need to establish a consensus. So here's a little example from a paper that I really liked, and mainly where I based my article on, is that in the past, or like still what a lot of people do, it's called the Walton model, is that they just label argument, so basically which consists of a claim and a conclusion, and then something which is non-argumentative. That's quite simple, right? I mean, that's not enough. And so they, from an NLP perspective, they suggest another way of annotating it, but then the question is, but will that be better? Again, this is something that they came up with the help of some lawyers, but then some other lawyers, will say, oh no, this is like completely useless and it doesn't work. And of course, there's a knowledge bottleneck, not enough open source corpora for training as well as for benchmarking, not many freely available studies, and Thanks.
Ooh, perfect timing. Yes. Let me tell you one more thing about Lisa. She has been also like an awesome contributor in the program committee of PyCon and PyData this year. Thank you very much. And a speaker. Yeah. So, yeah, thank you very much. So,
thank you.
I think that's now. Oh, yeah, I need the microphone. There you go. So, yeah, Uwe, it's time to say goodbye now. I think so. So, I need to go to the browser, I guess, and probably. Oh, no, I don't need my glasses. Okay, here you go. And where we are. Oh no, sorry. Okay, that's a little recap. So what you experienced, everything you experienced today. So, next, actually, PyData Kaiserslautern. I think that's next, right? Oh no, actually it's join our LinkedIn group, but who's not in our LinkedIn group? Oh, everyone, okay, interesting, okay. All right, yeah, call for speakers. You see, you can just start with a lightning talk, yeah, to share your knowledge, something you've experienced. So we have a Google form, just reach out. Sign up for lightning talks is always for the forthcoming meetup. So, but if you want to propose a talk, you can also propose it for a later meetup. Also, like proposing a full talk is very welcome and a really nice way to contribute back to this community. Yes, and if you need any help, feel free to reach out to us organizers. We can already also help you preparing a talk, or just tell you, okay, it's not as hard as you think. Yeah, it's basically most problems are in your head anyway. You will be awesome. Next is PyData Kaiserslautern. This was actually never planned until Uwe said, oh yeah, we can do it. The Fraunhofer ITVM, WM, we can do a meetup there. And I said, okay. We were actually thinking about, yeah, Stuttgart is the final frontier for us, and then we never wanted to go to Rhineland-Palatinate. But okay, now we are, but it's an excellent tech hub, so I'm really looking forward to it, and I'm really happy we have two awesome speakers. We have Catherine Jamour. She's the author of Practical Data Strategy, and she also wrote a book, I think 10 years ago, about data science and Python, which is also was very popular. She's a serial keynote speaker, so I'm really happy she will join us for this meetup. And we have Patrick talking about creating dashboards with Streamlit. And yeah, stay tuned. Maybe if you want to join driving together to Kaiserslautern, because it's a little from here, it's probably a little bit far, but definitely worth the travel. So yeah, so your turn, give us feedback, contribute a lightning talk. If you or your company wants to host us, just ping us. We're always looking for hosts. You can reach us on social media or just send an email to pydata.sw@pioneershub.de, and you can also just come and talk to us. Thanks to sponsors Quantco, the different food, which was great, in my opinion. Thank you. And yeah, Pioneers Hub for organizing. Thanks to our speakers. Thanks to our lightning talk speakers. Thanks for hosting. Thanks for video ops. Thanks for asking questions. And yeah, that's it. Thank you for being part of PyData Karlsruhe. Thank you.